In this lesson, we will try to solve a very famous problem in number theory that forms the basis of some of the most famous algorithms in cryptography. And the problem is to calculate modular exponentiation. Now, in a previous lesson, we had seen or devised an algorithm, an efficient algorithm for exponentiation, which was calculating x to the power n for two variables x and n. Modular exponentiation is the remainder upon dividing x to the power n with another variable, another positive number m. So x, n and m are three positive numbers here, and we want to calculate x to the power n mod m. So let's pick up some example. Let's say x is equal to 5 and n is equal to 2, and we want to take a modulo by 7, so m is equal to 7. So this will be equal to 25, and we can also use this particular sign that we use in a programming language for modulo, and it will be equal to 4. The remainder upon dividing 25 by 7 is 4. Similarly, if we want to calculate 5 to the power 3 modulo 7, it will be equal to 125 modulo 7, which will be equal to 6. So one simplest approach is that we can first calculate x to the power n and then take a mod by m. But there is a practical problem here. Even for small values of x and n, x to the power n can be really large, and it may not fit in a data type of the language. For example, integer is often stored in 32 bits, and 1 bit is for representing the sign. So the value ranges from -2 to the power 31 to 2 to the power 31. So if we want to calculate 2 to the power 100, say, then it will not fit in an integer variable. We can have a variable like long or double that stores higher values, but still they will not be good enough to store x to the power n, even for some moderately high values of x and n. Now we want to calculate x to the power n mod m. Let's see what we can do here. Fortunately, all these laws of associativity, commutativity and distributivity that apply to normal arithmetic also apply to modular arithmetic. So for example, a into b modulo m is equal to a modulo m into b modulo m and an overall modulo m of this particular expression. So for example, if we want to calculate, say, 5 into 7 modulo 3, then it is simply equal to 35 modulo 3. So upon dividing 35 by 3, the remainder would be 2. Now let's try to solve this using the expression in the right hand side. So this will be equal to 5 modulo 3 into 7 modulo 3 and an overall modulo 3. So 5 modulo 3 is 2 and 7 modulo 3 is 4. So this will be 4 into 2 modulo 3, which is 8 modulo 3, and again this is equal to 2. And you can pick up some other values of a and b and validate that this is true. Now here we can write x to the power n as x into x to the power n minus 1. So this overall expression would be x into x to the power n minus 1 modulo m. So we can also write this as x modulo m. So here a is x and b is x to the power n minus 1 into x to the power n minus 1 modulo m and an overall modulo m. And I'll clear some of this calculation in the left. So again, if n is even, then we can write x to the power n as x to the power n by 2 into x to the power n by 2. So this expression can also reduce to x to the power n by 2 modulo m into x to the power n by 2 modulo m and an overall modulo m. So we have a recurrence relation here once again. So I can write, and I'll write this in a little neat manner, x to the power n modulo m is equal to x to the power n by 2 modulo m into x to the power n by 2 modulo m overall modulo m if n is even. It is equal to x modulo m into x to the power n minus 1 modulo m overall modulo m if n is odd, and it is simply equal to 1 for n is equal to 0. Now this recurrence relation is very similar to what we had used to calculate x to the power n in the previous lesson. So n is equal to 0 is our base case, and for n even and n odd we have two different recurrence relations. Now let's write a program, a function to implement this recursion. Let's say we write a method mod that takes as argument x, n and m, and it goes like this: if n is 0, simply return 1, else if n is even, which is the same as saying n modulo 2 is 0, then first calculate x to the power n by 2 modulo m. So we make a recursive call to calculate x to the power n by 2 modulo m, and then we return y into y modulo m. Once again, instead of writing these two expressions, we could have written return mod of x to the power n by 2, x to the power n by 2 mod m into x to the power n by 2 mod m overall mod m. But in this case, we would unnecessarily make two recursive calls. So we would unnecessarily calculate the same value twice, which is very bad. So we calculate this x to the power n by 2 mod m once and store it in a variable, and then return y into y modulo m, where y stores this value. Now if n is odd, then in that case we simply return x modulo m into x to the power n minus 1 modulo m, which is calculated by this recursive call, and an overall modulo m. So this gives us a recursive algorithm to calculate x to the power n modulo m, and this algorithm to calculate modular exponentiation is very similar to the previous algorithm that we had shown to calculate x to the power n in our previous lesson. The time complexity for this algorithm is order of log n, or big O of log n. We will try to deduce that how this time complexity is order of log n in another lesson. But nevertheless, log n time complexity is the best time complexity to have. So thanks for watching.